Hello everybody, and welcome to the continuation of page 22 in the workbook. And in this video we're going to talk about a second way of approximating area under a curve. This method is called the midpoint rule, and you probably saw this technique already in Calculus 1. We're going to spend a minute just to review it here. Okay, so again, we've got a function that we're trying to estimate the area underneath between A and B. Okay, and this time, instead of using trapezoids, we're going to use rectangles. You can kind of see the rectangles have already been drawn into the picture for us over here to the right. And what I want you to pay attention to is where those rectangles are touching the curve. Okay, for example, the first one, notice that if you follow it down, it's touching at the middle point, and I'm going to give a name to that middle point. I'm going to call it x1 bar. Okay, maybe sneak it into the picture there. And that's true for all of these rectangles. Notice that they're all hitting the curve in the middle points. Okay, and we'll give each of the middle points the names x2 bar, x3 bar, and so on, all the way until we get to the last one. Okay, and those are points that are just halfway between our partition points. So in general, notice that you could get x1 bar by taking the average of x0 and x1. It's halfway in between. And so we get kind of a general formula for the midpoint that looks like this. Okay, I'm just going to write it down because it emphasizes that it's the point in the middle. And what we'd like to do now is to write down a formula for mn. Okay, in words, what that represents is the midpoint rule with n rectangles. Okay, and it's also a way of estimating area underneath a curve. Okay, how would we measure the areas of those rectangles? Well, let's start with the first one here. Okay, so the area of a rectangle is just its height times its width. Okay, and we're taking delta x to be the width of one of our rectangles, just like we did in the trapezoid rule. So we need to take the delta x and we need to multiply it by its height. And notice that you can get the height by taking this middle point and just substituting it into our function. So in a nutshell, what we're going to get is f of x1, whoops, not I, I'm sorry, 1 bar, and then we're going to multiply it by its width. Height times width gives us area. And then we move over to the second rectangle. That's the one that looks like this. And its height is going to be f of x2 bar times delta x. And we just keep going until we get to the very last rectangle. And then we might notice that there's a delta x in every single one of these terms, and so it's customary to just factor that delta x out and rewrite our formula like this. Okay, whoops. All right, and I'm going to box that in. This is a second way of approximating the integral, just using rectangles this way. This time. Okay, so far in this section, what we've done is kind of derived or described two formulas, two ways of estimating area under a curve, and in future videos we will demonstrate how to use these formulas to actually approximate the value of an integral.